Alright, welcome back. This is Chapter 8 Worksheet problem number 3. We have a member here with a rectangular cross-section, and we need to find the state of stress that the loading produces at point C here on the cross-section and here on the beam itself. Alright, so we have 2D rigid body equilibrium here, pin connection at A, roller support at B, and again rectangular cross-section. Now let's think about how we're going to solve this. So similar to the last problem, number 2 on the Chapter 8 worksheet, and like most of these combined loading problems, we're going to start by drawing our free body diagrams to find our reactions and internal resultants. And then we're going to look at how those internal resultants produce stress on the cross-section itself at the point that we're concerned with, which is point C. Right? So free body diagram of the whole beam. Use your equations of equilibrium to find your reactions. Once you have those reactions, you can make your cut into your beam, expose your internal resultants. Your normal force here acting to the right in tension is positive sign convention, V going down, and M bending upward. Okay, sum your forces in the X and Y to get your normal force and your shear force, and sum your moments about the cut to find your internal resultant moment. Once you've found those three values, we can now actually look at the cross-section at C and look at the stress that's going to be caused by these internal resultants. Okay, so this was all just statics, so that we can get into the mechanics and materials part and do some combined loading. All right, so at C here on our cross-section, I redrew our coordinate axes where Y is still going up here, but now Z is going to be going to the left, and X is going to be coming out of the page. So that's your right-hand coordinate system, and I drew the moment we found here, this 32.89. That's going to be about the Z axis. Right? When we're in the XY plane, the rotation here is in the Z direction. Your moment is about the Z axis. So I use this double arrow symbol to signify that. It's just a little neater to work with than the rotational arrow when we're looking at the cross section here. And so we can just break it into looking at NV and M separately. Our uniform normal stress distribution due to that N internal normal force is going to be our axial normal stress, N over A. And we had a compressive normal force here because we got a negative value. Okay, we assumed a positive tensile force. We got a negative, which means it's actually compressive. So our axial stress is going to be negative. The area is a rectangle. We get an axial normal stress of negative 1.32 megapascals. Okay, so that one's pretty straightforward. Now let's look at our transverse shear stress due to that tangential V force here. Right, so we're going to use our shear formula, VQ over IT, but since we're up here at C, at our outer surface, we know that our shear stress is going to be 0 there. Why is it 0? Well, basically because this Q value is going to be 0. Q is our Y bar prime times A prime. A prime doesn't exist up here. There's no other material for that moment of the area to exist, so Q is 0, so our transverse shear is 0. You know, in the end, it's helpful to just know that if you have your neutral axis here, your shear stress is going to be 0 at your surfaces away from that neutral axis. So down here also, your transverse shear is 0. Anywhere up here, it's also 0. All right? We know that we're not going to have any torsional shear stress either because, one, there's no torque about the x-axis, but also we don't consider torsional shear in this class about rectangular cross sections. We only look at circular ones, right? But then we have to look at our bending stress. Finally, that's our last type of stress. That's going to be our flexure formula, my over I, and I wrote in mz because we're bending about the z-axis. You could have a bending moment about the y-axis, but we don't here in this 2D problem. The y distance, I wrote here, is equal to our c value, lowercase c. That's our distance from our neutral axis to our outer surface. That's 125 millimeters. Plug that in, get 0.125 meters. plug in our positive moment that we found. The negative sign takes care of whether it's going to be compressive or tensile. Turns out it's going to be compressive, right? We don't have any other negative signs to cancel it. And don't forget your moment of inertia about our neutral axis here, 1/12 BH cubed. B is 50 millimeters, H is 250 millimeters. You get a bending normal stress of 63.16 megapascals. Again, the negative sign says compressive. If you follow all the sign conventions, the negative signs will take care of themselves. Then when we do our superposition to find our resultant of these two normal stresses, they're both negative, so they add together and we get a normal stress of negative 64.5 megapascals, so compressive. And again, our shear stress was 0, so our stress element is going to look something like this. X-axis is going to the right here, so we have a compressive normal stress on the X face here, and then for equilibrium on this X face on the other side, and no shear stress arrows anywhere because it's 0. All right, that's it for that problem. I'll see you on the next one.